The next interesting generalization comes about when we start to consider non-adiabatic effects within the thermal equation. Namely, what happens when fluid parcels are able to exchange heat between each other. And these non-adiabatic effects are very important for understanding the possible equilibria of systems as we consider basic balances in our fluid systems. So let's write down our thermal equations. So the adiabatic portion of the thermal equation, d by dt of u plus u dot grad t plus gamma minus 1 t times the divergence of u equals, and now when we include non-adiabatic effects, we generally they come in as a 1 over rho minus 1 over rho times the divergence of q, where the q are the vector fluxes of heat. In this system, right, this first part here, this is the Lagrangian derivative dt dt. This is how heat temperature changes by motions in the fluid, just carrying it around and advecting it. This set of terms here, this is how things change from compression or expansion. And then these terms here are the non-adiabatic effects. Non-adiabatic just means that the heat and entropy of the system can change from these effects. If we want to consider the simplest form of non-adiabaticity, if the fluxes are entirely from diffusion, if Q are diffusion of heat alone, then we typically adopt a Newtonian model of cooling, essentially, Q, and the flux of heat is given by negative times K times grad T. And this is a heat diffusion coefficient. And it has units of mass per length per time. Mass per length per time. Okay. And as you can see here in a diffusion-dominated system, bigger diffusion coefficients mean more flux of heat, and bigger temperature gradients mean more flux of heat, and the heat is always, the flux of heat is always in the opposite sense of the temperature gradient itself. Sometimes we write K in another form. I'll write that here briefly. K, with these weird units of mass and length and time, this can be written in a slightly more familiar unit that we'll see at various times. If we take a factor of density out, and this chi here, this is the thermoelectric diffusion, thermoelectric diffusion coefficient. And what's nice about the thermoelectric diffusion coefficient is this has units that are a little more useful for dimensional analysis. It has units of length squared per time, which end up being the same units as viscosity, which we'll meet later in the momentum equation as we consider friction in the momentum equation. This is just a linkage between these concepts. For now, we'll talk in terms of just the general capital K diffusion coefficient to get some intuition for the properties of this system. All right. So with our non-adiabatic system here, let's now consider thermal and hydrostatic equilibrium. So what we're going to look for here are solutions where we have d by dt goes to 0. That's the equilibrium bit. And we're also going to consider hydrostatic solutions, so ones where there's no motion. So if we write our temperature equation again, d by dt of t plus u dot grad t plus gamma minus 1 t div dot u is equal to minus 1 over rho div dot q. I'll go through and put on some vector signs here. Under equilibrium, this term is 0. This is for the equilibrium. And then our velocity-related terms are 0, and these are because of hydrostatic assumption. So for a system in thermal and hydrostatic equilibrium, our balance equation is that the divergence of the heat fluxes are 0. So that's our equilibrium equation. We can rewrite this in a useful way by putting in our diffusion approximation. So this means that if we're diffusively dominated, that the divergence of k grad t is equal to 0. So there are a couple ways that this can come about. Let's consider some simple cases. How can we satisfy that the divergence of k grad t is equal to 0 everywhere and always? Well, a first simple case is to just say that the gradient of t is equal to 0. If the gradient of t is equal to 0, then anything times it is equal to 0, and the divergence of that is equal to 0. So if the gradient of t is equal to 0, we have a thermal equilibrium solution. This, of course, implies that if there's no gradient of t, that t is constant. And this then implies that we have an isothermal atmosphere, an isothermal fluid. And iso, same everywhere, thermal, temperature, isothermal fluid, the name tells you that the temperature is constant. So that came from setting that grad t was constant. Okay, we can make a slightly more complicated case. We can say something like, well, what if k is constant, and what if grad t is constant? Now we have if they're each independently constant, what do we get in that kind of case? Well, now grad t, right? This is some constant, say C1 divided by k. That implies that our temperature, it has an integral solution from grad t, and the temperature just has a simple form. It's got a C1 over k times whatever our integration direction is, say z, and then plus some other constant, call it C0. We have some simple linear form for the temperature. This is, of course, assuming that we have a plane parallel atmosphere, so that our divergence operator ends up just having a simple expression. Things can change a little bit in curvilinear coordinates like spheres. This is a linear temperature profile in something like a plane parallel atmosphere. It's got a simply expressed temperature profile in things like spheres. And these are the polytropic fluids and the polytropic atmosphere solutions. Now, are there any other cases that we can solve? There's one other case that we can solve, and that is when this is a special case, but one that has some real importance. When k is not constant, and when grad t is not constant, so they both vary, but the combination k grad t is constant. That can lead to a thermal equilibrium, right? Because again, so div dot k grad t is now equal to 0, so we have thermal equilibrium. And if our k is a function of temperature only, even if it's a nonlinear function, then we have a system that we can actually solve. We have a nonlinear system, k grad t equals const with nonlinear k. That's a potentially solvable system. So in this system, we can also obtain the thermal equilibrium. And what's important is that in all of these, we've figured out a thermal equilibrium, an isothermal profile, a linear profile, a more complicated profile, and we've done that only on functions related to the temperature. We haven't brought in any information about gravity in the system, the density patterns in the system, or any other forces or balances in the system. All of these simple systems, we can calculate the temperature profile all by itself with no other information, and then we can use that to solve a more interesting and larger system in a decoupled fashion, which simplifies the solution.